Hi, and welcome to this video where I'll walk you through the answers to the bike sharing data analysis using Python and Neo4j. In this assignment, we're using Python and VS Code to create nodes and relationships in Neo4j, modeling trips, bikes, stations, and members in a graph structure. We'll then run queries to extract insights from the data, like identifying popular stations, calculating trip durations, and more. Let's get started with the first question. In question 1, we are asked to add relationships between the trip and the bike, and the trip and the member using data from the bike number and member type columns. First, I use the edges.append function to create a relationship between the trip, represented by trip score ID, and the bike, which is represented by the row bike number. This relationship is labeled as used, indicating that this specific bike was used during the trip. Next, I add another relationship between the trip and the member type, represented by row member type, using the edges.append function again. This relationship is labeled as subscribed by, meaning the trip is associated with a specific member type. These two relationships are essential for capturing how each trip is connected to both the bike and the member in the graph database, which will help us perform future queries and analysis. In question 2, we are tasked with writing a cipher query to create nodes in Neo4j using the unwind and apoc.create.node functions. The query is designed to process a batch of node data and create nodes based on the type of entity, either a trip or another type of node like a bike or member. The query starts with unwind.batch as node data, which iterates over each element in the batch, allowing us to process them individually. Next, we use call apoc.create.node node.data.type, which dynamically creates nodes with the label corresponding to the type of data. For example, if node.data.type is trip, it assigns the trip label to the node. The case statement is used to differentiate between the types of nodes. If the node is a trip, the function apoc.map.clean is used to create a clean map with key attributes like ID, duration, start date, and end date, essential details for trip-related nodes. If the node is of any other type, the query simply uses name as the key attribute. Finally, the yield node returns the created node, allowing us to inspect it. This approach efficiently processes each node in the batch and ensures that nodes are created with the appropriate data structure for each type. In question 3, we are asked to write a cipher query to create edges or relationships between nodes in Neo4j. We use the unwind clause to iterate over the batch of relationship data and the apoc.create.relationship function to establish the connections between the nodes. The query starts with unwind.batch as edge data, which processes each item in the batch of relationships. Next, we match the source node, which in this case is always a trip node. We do this by using match source trip edge data.source, where edge data.source is the ID of the trip. Then, we match the target node, which could be a station, bike, or member node, based on the name of the target. This is achieved with match target name edge data.target. Once both the source and target nodes are matched, we use call apoc.create.relationship source edge data.relationship target to create the relationship between the two nodes. The type of relationship is dynamic and is specified by edge data.relationship, for example, UST. For bikes, or subscribed by for members. The in the function indicates that we are not passing any additional properties for the relationship. Finally, the yield rel clause returns the created relationship so we can inspect it and ensure it's been created correctly. Now that we've inserted the data into Neo4j, let's take a look at the graph visualization to confirm that the nodes and relationships were created correctly. Here in Neo4j, you can see a representation of the bike sharing data. Each color represents a different type of node. The orange nodes represent stations. The blue nodes represent bikes. The purple nodes represent trips. The light red node represents a member. The relationships between these nodes are displayed as arrows. For example, the arrows labeled started at and ended at connect trips to their respective starting and ending stations. The arrows labeled used show which bikes were used for specific trips, and the subscribe by arrows link trips to the member type associated with that trip. This visualization helps us see the structure and relationships in the dataset, confirming that the data has been correctly modeled in Neo4j. Now that we've confirmed the relationships between trips, bikes, members, and stations are in place, we'll proceed with analyzing the dataset by querying it in the upcoming questions. In question 4, we are asked to find the top 10 most popular start stations for bike trips. To achieve this, I wrote a cipher query that first matches trips to their corresponding start stations and then counts the number of trips that started at each station. The query begins with match, trip, started at attach, station, station. This line matches all trip nodes that are connected by the started at relationship to a station node, identifying where each trip began. Next, we use return station.name as station name, count trip as trip count. This part returns the name of each station and counts how many trips started at that station, aggregating the results by station name. To get the most popular stations, we use order by trip count desk to sort the stations in descending order by the number of trips, so the most popular stations appear first. Finally, the limit 10 ensures that only the top 10 stations with the highest trip counts are returned. This query provides a quick insight into the most commonly used start stations in the dataset. In question 5, we are asked to find the top 10 most popular end stations for bike trips. This is similar to question 4, but instead of start stations, we focus on end stations. The query starts with match, trip, ended at, station, station. This line matches all trip nodes that are connected to a station node through the ended at relationship, indicating where each trip ended. Next, we use return station.name as a station name, count trip as trip count to return the name of each end station and count the number of trips that ended there. To identify the most popular end stations, we sort the results with order by trip count desk, ensuring that the stations with the highest number of trips appear first. Finally, the limit 10 clause ensures that we only retrieve the top 10 most popular end stations based on trip count. Question 6. The goal is to find the average duration of bike trips for each member type. This can give us insight into how different types of members use the bike sharing service. The query starts with match trip, that's subscribe member, which matches all trip nodes that are connected to a member node through the subscribe by relationship. This indicates which member type took each trip. Next, we use return member.name as member type, avg trip.duration as avg duration to return the name of the member type and calculate the average duration of their trips using the avg trip duration function. Finally, we order the results by average trip duration in descending order using order by avg duration desk. This allows us to see which member types have longer or shorter average trip durations. This query helps us compare the usage patterns between different member types, providing valuable insights for optimizing the service. Question 7. We are asked to find how many unique bikes were used in the dataset. To do this, we can use a cipher query that counts the distinct bikes. The query starts with match bike bike, which matches all the bike nodes in the graph. Next, we use return count distinct bike as unique bike count to count the number of unique bikes. The distinct keyword ensures that each bike is only counted once, even if it appears multiple times in the dataset. This query provides the total number of unique bikes used across all trips, giving us a measure of how many different bikes were active in the bike sharing system. Question 8. In question 8, we are asked to determine how many trips were taken by each member type. This helps us understand which member types are most active in using the bike sharing service. The query starts with match, trip, chash, member, member, which matches all trip nodes connected to member nodes through the subscribed by relationship. This tells us which member type is associated with each trip. Next, we use return member.name as member type, count trip as trip count to return the name of each member type and count how many trips they have taken using the count trip function. Finally, the order by trip count desk clause sorts the results in descending order, showing the member types that have taken the most trips at the top. This query provides a clear breakdown of trip counts by member type, which can be useful for analyzing member engagement. Question 9. In question 9, we are asked to find the top 10 most used bikes for trips. This will show which specific bikes were most frequently used in the bike sharing system. The query starts with match, trip, trip, bike, bike, which matches all trip, nodes that are connected to bike nodes through the used relationship. This indicates which bike was used for each trip. Next, we use return bike.name as bike score name, count trip as trip count to return the name of each bike and count how many trips were taken using that bike with the count trip function. To identify the most used bikes, we use order by trip count desc to sort the bikes by the number of trips they were involved in, showing the most used bikes first. Finally, the limit 10 clause restricts the result to only the top 10 most used bikes. In question 10, we are asked to print the routes taken by a random bike. In this case, I chose the bike with the highest number of trips from question 9, which is W21No72. The goal is to display the route details for each trip this bike took, including the start and end stations and the trip's start and end times. The query starts by matching the selected bike using match bike name random bike trip trip trip, which finds all the trips where the bike W1No72 was used. Next, we match the starting and ending stations for each trip. Match trips started at Jatch. Start station station matches the station where each trip started. Match trip end station matches the station where each trip ended. We then return the trip details using return trip.id as trip ID, start station.name as start station, end station.name as end station, trip.startDate as start date, trip.endDate as end date. This returns the trip ID, the names of the start and end stations, and the start and end times of each trip. Finally, we use order by trip.startDate to order the trips by their start dates, showing the routes in chronological order. This query allows us to trace the routes taken by the selected bike and understand its journey patterns across multiple trips. To conclude, we've used Python and VS Code to create a graph structure in Neo4j and run queries to analyze a bike-sharing dataset. By leveraging the combination of Python scripting and Neo4j's graph database, we were able to efficiently model trips, bikes, stations, and members, and extract useful insights like popular stations, bike usage patterns, and trip durations by member type. This approach shows the power of using Python for automation and Neo4j for handling complex, interconnected data. Thank you for following along with this walkthrough, and I hope it provided a clear understanding of how to work with Neo4j using Python.